This is question 13 from the LO1 tutorial sheet for engineering dynamics. This is an example of a question where we need to use the graphical method, or as this question calls it, the geometrical method, to find the resultant vector acting on a body which has 4 different vectors acting on it. Now, in order to do this sort of problem, we can just jump straight in to solving the question and to drawing our vectors into the vector diagram, which will help us to find the answer. But sometimes it's always useful to draw a free body diagram to get the information from the question. I'm going to do a very rough diagram here. I'll put an axis. I won't worry too much about making this diagram accurate, because this is just going to tell us where all of the different vectors appear in the question. So here's my x and my y-axis, and because we're told in the question that we have directions, a compass, we'll label these as north, south, west, and east. I put an arrowhead for the positive direction in each case. So let's see what we have, and I'll draw these in roughly. And what I'll do in this example, I'll use a different colour for each of my vectors. Now, of course, there's no need to do this when you're doing a question in the TMA or in class, but sometimes it's helpful in the videos to make them stand out. So we're told, first of all, we have a vector acting 12 kilometers per hour due north. So I'm going to draw a line in red here. It's meant to be acting straight up. We arrow to show the direction of due north, and I'll label that as 12 kilometers per hour. We're next told that we have a vector acting 30 degrees east of north. That means pointing north, we move round 30 degrees, and that's 15 kilometers per hour. So it'll look a bit like this. Now, this is not being drawn in exactly, but it's saying that this angle here, this is 30 degrees east of north, and that's 15 kilometers per hour. We're told also we have a vector acting at 40 degrees east of south. So again, that's if we're pointing straight south and we move towards east by 40 degrees. So something that looks a bit like this. So this angle here is 40 degrees, and I'll mark that in. Saying this vector is 20 kilometers per hour. And lastly, in purple, I'll draw a final vector, and it's acting due south. That means a line straight down the way. Direction is important as well, so it's a straight vertical line, but an arrow pointing down, and that's 12 kilometers per hour. So we have 4 vectors, and we want to find the resultant velocity, what's the combination of these 4 vectors. So in order to do this, we're going to use the graphical method. And we'll always start our graphical method by setting a scale, because we have to draw these vectors proportionate to how the size in terms of kilometers per hour. So the 12 kilometers per hour vectors should be the same length, although in different directions, and the 15 and 20 should be bigger, proportionate to the size we draw on the paper. So I'm going to say, because of the size of the page I'm working on, I'm going to make one of these little intervals in my ruler, so maybe a centimetre on your page. I'm going to make this distance here, and I'm going to say this represents 2 kilometers per hour. So I wanted to draw my first vector, which we'll be doing shortly. It'll be 6 of those to length, because they are all 2 kilometers per hour. Now, the next step is to pick any one of our vectors and draw it to scale in the direction it's currently pointing. This question, and any question like it, can be solved by picking any vector to begin with and proceeding through them in any order. But I tend to find that it can make life easier to start at the top and work clockwise, because sometimes, not guaranteed, but it involves that our vectors won't cross over each other, but they might well do. But as a spoiler, they don't in this question, so that's why I'm picking it here. So I want to start off by drawing this first vector, first in the list and first when I drew. So it's 12 kilometers per hour acting north. Now I've said one interval is 2 kilometers per hour, so I had to draw 6 intervals here to mark 12 kilometers per hour. So I do my best to draw that as exactly as possible. So it is vertical, just like the just like in the free body diagram, that's exact to scale. I'll put a little arrowhead on it, trying to make sure we do it right at the end of the line here to indicate the direction as well, because the direction will be important at every stage. Now, how we proceed is we take our next vector, and rather than drawing it from the same starting position, we shift it so it starts at the end of our vector we've drawn already. Now, the next vector is a blue vector, which is acting 30 degrees round from north. So what I can do is I can add a little north line here just to help us measure our angle. So a wee dotted line here. And what you'll be doing with your protractor just now is measuring an angle between that line and moving to the right of 30 degrees. Now, I can't demonstrate that here, so I'm doing this with my ruler. So I started at 90 and I've moved round to 60. 90 minus 60 is 30. So I line up my interval with the edge of the red vector, and I need to draw a line which is 15 kilometers per hour in size. Well, if each interval is 2, that means I need 7.5 intervals. So I'll do 1, 2, 3, 4, 5, 6, 7 and a half. So that represents 15 kilometers per hour. Now I want to mark some of these things on to keep myself right. So I can mark on here 15 kilometers per hour. I can also indicate this was a 30-degree angle. And I probably should have put at the beginning, this was, I'll put it in red so it's the same color. 12 kilometers per hour here. And of course, a little arrowhead at the end of this blue vector to show that it's acting in that direction, 30 degrees from north in the easterly direction. So the 2 vectors down, 2 to go. The next vector I'm going to add is the green vector. Now, I'll put my dotted line on here again so we can measure. So we know if we have a vertical line coming down the way, which is the direction of south, I'll put this in as a dotted black line here. Then if we go round 40 degrees, so I'm 90 pointing down the way, if I come round to 50, I've moved around 40 degrees from that point. Then I'm going to measure an angle of 40. So in your protractor, you'd be setting it along that dotted line and measuring around 40. So I can only do 90 minus 50 here to get 40 in mind. So if you're unsure about how to use the protractor measurements, remember there is a separate video where I do a different problem, but I film it with the protractor so you can see how it's done in that method. So I've measured round 40 degrees from the dotted line, and I want to draw in this green vector. Now, it's 20 kilometers per hour, so it's going to be 10 of my intervals. So I'll draw them in just now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that's not too bad. And so I'll draw a wee arrowhead in here as well. I'll mark on the size of the vector, 20 kilometers per hour, and also marking that angle as well. That was 40 degrees I measured round, and you can see how that compares to the 40 degrees on the free body diagram. The last thing I have to do is a bit easier. I don't have to measure any angles here to make my ruler nice and straight. This is easy for me to do on the whiteboard. So usually using the edge of your page to keep things nice and straight, or even better if you're using squared paper, you're able to make sure that you are lining things up nice and neat. You've not got a slanted line taking you off track. So I've lined mine up with the end of the previous vector. But on my free body diagram, it's the line coming straight down, so I need to make mine straight down. It's 12 kilometers an hour, which is equal to 6 of my intervals. So I'll draw in 2, 4, and 6. I'll draw a little arrowhead there as well. And of course, this is 12 kilometers per hour. So what we've done is we've taken these 4 vectors that were on the diagram on the left, what our question told us existed. We've drawn each one to scale, so the same length as the value say. The 2 12s are the same length, the other ones are longer, but we've run to scale. And we've drawn them all pointing in the direction that they were due to be pointing at the question. You see that blue one's pointing up and to the right, green one's pointing down and to the right, the red one's pointing up, and the purple one's pointing down. But all we've done differently is we've joined them on tip to tail. So from one arrowhead, we start the next vector from there, we work our way around. We've got our starting point at the beginning of the red vector and our end point at the beginning of the purple vector. Now this is how we find the resultant vector, the overall velocity acting in this body. We take our ruler and we draw a line right from where we started, so the start of the red vector, and we join it to the end of the purple vector. Now, let's have a look. I think maybe about 6 degrees looks about right here. Remember, this is 6 degrees below the horizontal line in the page. So I'll just use black, not use this colour at all, and I'll draw this line in along here. So it'll be a bit different for you, because what you'll do in paper is you'll draw in the vector first. And I should say, before I take away the rules now, I should say you'll have a little arrowhead, because we're showing that we're coming from the very starting point to our very end point here. So you're drawing a straight line, and then what you do is measure it. So I'm going to line up my ruler as best I can, and it looks to me like I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and a bit intervals here. So that looks about right. We'll say 2, 4, 6, 8, 10. It's not quite 10 and a quarter, it's maybe 10 and an eighth. So that would be 20, something like 22 kilometers per hour. It's not going to be very accurate in the diagram I've got here. We'll mark that and we'll say, we'll call it 22 kilometers per hour. And of course, we saw that our angle downwards is 6 degrees. So if I take a line back up to the top, and also dashed line in here. We can mark on our diagram that we've measured this to be 6 degrees. Now these things will vary a little bit. If you do this same problem by hand, you might even find it varies by a couple of degrees or a couple of, I should say, kilometers per hour, because it's hard to be precise, particularly when we're making multiple measurements, but it should look a bit like this. And of course, when it comes to assessing, there's definitely a margin for error, which is factored into the answers. So I hope this has been of some help. It is slightly harder to demonstrate when we're using the whiteboard here, but as I mentioned, there is an example using pencil and paper, which you can follow along with the course notes as well.